Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
If you've ever tried to wrap your head around how the internet actually works, you know the feeling. Information overload hits fast and hard. You're just drowning in acronyms and protocols before you even get past what a router is.
It's so true. And what's really wild is that the core job of the internet, getting data from you to, say, a server across the globe, it all relies on millions of tiny decisions made every single second. It's kind of like a massive global postal system, but the roads are changing constantly.
Right. And that's our mission for this deep dive.
Yeah.
We want to cut through all that noise and give you a shortcut to understanding how those decisions get made. We're unpacking the rules the routers follow. Routing protocols, or RPs.
Think of them as the digital rules of the road. At its core, a routing protocol is just a defined set of rules. It tells routers how to talk to each other so they can pick the best path for data to travel.
And this is a really crucial point to get right up front, because I think this is where a lot of confusion comes from. The routing protocols. They aren't the delivery trucks. They don't actually move your data packets.
Exactly. They are pure pathfinders. Their only job is to update the routing table, which is basically the router's internal map. Their whole purpose is to make sure that map has the most efficient, the fastest route available at that exact moment.
So when your data packet shows up, the router just looks at the map and knows exactly where to send it next.
Precisely. The data delivery is the data plane, but the RPs, they live in the control plane, just constantly updating that map.
Okay, so map making. That starts with the very first decision a network admin has to make, right? Is it, do I draw this map myself, or do I let the routers figure it out automatically?
That's it. That is the fundamental split between static and dynamic routing. Static routing is the totally manual, handcrafted option. The administrator literally types in the exact path a packet has to take. It's rigid.
And on the surface, that sounds, it sounds like a good thing for small setups, maybe, where you want total control and predictability. What are the actual benefits of doing it that way?
Well, for one, there's no overhead on the router's CPU. It's not thinking, it's not calculating, so it saves power. And it's very secure because only the administrator can add or change a route, no one else.
So for a tiny, stable office network, it could work.
It could, but the disadvantage is just they scale up so fast. As the work grows, that manual work becomes a total nightmare. The admin has to know every single connection.
Which is just not practical for a big company.
Not at all. And here's the real weak point, the aha moment. Resilience. If a single one of those manually defined links fails, the whole path is just gone. The network goes down.
The system has no backup plan.
None. The administrator has to physically log in and reroute everything by hand. That's just not going to fly in a world where links are failing and coming back up every minute of the day.
That lack of resilience, it brings us right to the gold standard then. Dynamic routing protocols. This is where the routers automate the map making. They talk to their neighbors, they share information, and they send out updates when things change.
And the benefits here are just night and day. It's so much easier to set up, even on a massive network. If a link fails, the protocol just instantly figures out a new way to get there. It can even do smart things like load balancing across multiple links to keep traffic flowing smoothly.
So dynamic routing gives us that resilience and scale that we need. But what's the catch? What's the cost of all that automation?
Resources. It's always resources. Those updates between routers, they consume bandwidth. And all those real-time calculations to keep the map accurate, that puts a real load on the router's CPU and its memory.
So it's a trade-off. You're trading processing power for ease of use and, I guess most importantly, for a network that doesn't just fall over.
That's the trade, exactly.
Okay, so once we've decided on dynamic, we hit another fork in the road. The actual logic behind how they choose the best path. And this gets us into the big one. Distance vector versus link state.
Let's start with distance vector, or DVR. The idea is pretty simple, but, well, it's also pretty inefficient. It's based entirely on hearsay. Yeah. A distance vector router just advertises its entire routing table to every single neighbor it's connected to. And it does this periodically, like every 30 seconds.
So it's like a rumor mill. It just blindly trusts whatever its neighbor tells it, and it makes its decision based on distance, which is usually just how many routers or hops away something is.
That's the philosophy, exactly. I trust my neighbor's map, so I'll use it. The problem is that it's constantly broadcasting the whole map. It uses a ton of bandwidth, and it's slow to react. If a link fails far away, that news has to ripple through the network one neighbor at a time. That's slow convergence. It can also lead to routing loops.
Where packets just get stuck bouncing between two routers that have bad information.
Exactly.
So if that DVR model is so brute force and kind of shaky, how did engineers fix that?
They moved from trust to intelligence. And that brings us to the link state routing protocol, or LSRP. A link state router doesn't just trust its neighbor's map. It gets a little piece of information from every router, and it uses that to build its own complete, accurate map of the entire network.
Wow, okay. That sounds way more detailed. How does it calculate the path then, if not just by counting hops?
It uses things like the actual speed of the path and the resource cost. It runs a really smart algorithm called shortest path first, or SPF. That lets it figure out the absolute fastest route based on real-world factors, not just proximity.
And to do that, it needs a much more complex system inside the router, right?
Yeah.
I heard link state uses 3 different tables.
That's a key difference. It maintains 3 databases. First is the neighbor table. Simple enough, just a list of routers it's directly connected to. Second, the topology table. This is the big one. It stores the entire network map, the best route, plus every possible backup route. It's the full picture.
And the third?
The routing table. This is the final output. It takes all the info from the topology table and just puts the single best route in there, ready to forward data.
So its big advantage is that it already has a backup plan ready to go in that topology table.
Precisely. And that's how it saves so much bandwidth. It uses what we call triggered updates.
Ah, okay. So instead of shouting its whole map every 30 seconds, like distance vector.
It only speaks up when something actually changes. When a link goes down, it sends out a tiny partial update with just that new piece of info. It saves a huge amount of traffic.
And it's less likely to create those routing loops because every router has the full picture.
Right. The trade-off is that it's a lot harder to configure and manage than distance vector.
That is a perfect breakdown. So we've gone from manual versus automatic, and now from hearsay versus a complete map. Let's connect this to the actual protocols people have probably heard of, the ones running everything from a home office to the internet backbone.
To do that, we have to talk about scale. There are interior gateway protocols, or IGPs, which run inside a single network, like a company's network. And then there are exterior gateway protocols, EGPs, which connect those huge networks to each other. That's what makes the internet the internet.
Okay, let's start inside with the IGPs. On the distance vector side, the classic one is RIP, right? The Routing Information Protocol.
Yep, RIP is classic DVR. It just uses hop count, and its biggest limitation forever was that it could only count up to 15 hops.
Which makes it useless for anything but a pretty small network.
Exactly. There's RIPv1, the old version, which was a broadcast protocol, super noisy.
And then RIPv2, which was a big improvement because it used multicast, sending updates only to other routers that cared, not to every device on the network.
A crucial update. But then you get into the commercial side of things. Cisco came along and saw RIP's limitations.
And they developed IGRP, the Interior Gateway Routing Protocol.
They did. IGRP was made specifically to beat that 15 hop limit. It's still distance vector, but it pushed the max hop count all the way up to 255.
A huge jump.
Massive. And it was smarter. Instead of just hop count, it used a complex metric with things like bandwidth, network load, and delay.
And from that, they built EIGRP, the Enhanced IGRP.
Right, which is what we call a hybrid protocol. It's kind of the best of both worlds. It uses some distance vector logic, but it also builds neighbor and topology tables like a link state protocol. Very powerful.
So that's the proprietary Cisco path. What about on the open standard, link state side?
That's where you find the champion. OSPF, Open Shortest Path First. This is the definition of a modern link state IGP.
And it uses that sophisticated Dijkstra algorithm you mentioned.
It does. It uses that to calculate the absolute shortest path whenever the network changes. It's also incredibly secure. You can authenticate updates to stop anyone from injecting bad routes.
So for a big corporate network, the choice is often between Cisco's EIGRP and the open standard OSPF.
That's often what it comes down to. But remember, none of these, not RAP, EIGRP, or OSPF, can route traffic between the huge domains that make up the internet. For that, you need an EGP.
And that brings us to the king, BGP, the Border Gateway Protocol.
This is it. This is the protocol of the global internet. We call it a distance path vector protocol. PGP is how huge networks, like, say, Google or your ISP, tell each other which IP addresses they can reach. It's not about speed, it's about policy.
And you mentioned something fascinating before, that BGP has no auto-discovery. In a world of automation, it has to be configured manually. Why?
Because BGP is as much an economic and political protocol as it is a technical one. The routes are based on business agreements. We'll only send our European traffic through this partner, or we won't accept traffic from this network. You can't let a machine auto-discover a route that violates a multi-million-dollar contract.
Wow. So auto-discovery would just override those critical business rules.
It would. So it all has to be done by hand, based on policy. BGP is the ultimate example of an EGP, sharing information across these massive, policy-driven domains.
That context is so important. Let's hit one last technical detail that I think ties all this together really nicely. Classful versus classless protocols.
Right. This is all about how much information is in the update. Old protocols were designed when IP addresses were split into rigid classes, class A, B, and C.
So a classful protocol, like the original RIPv1 or IGRP, never sends the subnet mask in its update. It just assumes everyone knows the default boundaries.
Which is incredibly inflexible for modern network design. By contrast, classless protocols like RIPv2, OSPF, EIGRP, they do send the subnet mask information. This allows for efficient, flexible network design. It's really a fundamental difference between legacy tech and current best practice.
That really does tie it all together.
Yeah.
The best protocols are classless, and they're either link state or hybrid, so they can be super efficient.
Yeah. If you want the final takeaway nuggets, OSPF is classless, link state, uses smart metrics, and has no periodic updates. Super efficient.
IGRP was the bridge. Classful, distance vector, broadcast heavy, but it solved the hop count problem.
And RIPv2 was the improved legacy. Classless, but still a distance vector protocol that broadcasts every 30 seconds.
So we've really traced the whole evolution, from manual timetables to dynamic automation, from blind trust to complete maps, and from rigid classes to flexible subnets.
And all of it is to guarantee a few key things: loop-free routing, fast recovery when things break, and the ability to scale to the size of the entire digital world.
Okay, so we've established that these protocols are the rules of the road. But let's end with something to think about, and it comes back to BGP. We said that BGP, the single most critical protocol for the entire global internet, requires manual configuration. It's driven by human policy.
Right. For a system that's all about blinding speed and automation, that dependence on human configuration, it's a fascinating potential point of failure. It really tells you something about the unresolvable complexity of the internet's core structure. It's economic and political as much as it's technical.
So here's the thought for you to take away. If an administrator at a massive telecom company, one of these huge autonomous systems, misses or delays a critical BGP update, say they fail to announce a new path or they forget to withdraw a pass that's gone down, what specific global chain reaction would happen before that human error is corrected and the traffic starts flowing normally again? That's something to mull over.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo, haven't you checked out our new book yet? Link in description.